So welcome back, everyone. Thanks for coming back. Today we're going to be kind of continuing on from where we left off last week with Python and stuff like that. And halfway through, we're going to be introducing data science and stuff like that. Yeah, without any further ado, let's get started. So just as a refresher, this is our tentative schedule. This could change, we don't know. But this is roughly an idea of what we plan to do and when to do it. So right now, today is February 14th, by the way. Happy Valentine's Day for those who actually celebrate it. Today we're going to be continuing the Python crash course, and then, as I said, the introduction to data science. And then next week, we're going to continue with that sort of, a view on data and stuff like that, how you're going to clean it, how you're going to manipulate it, how you're going to, handle null values, stuff like that, and how you're going to feature engineers that are actually useful in your machine learning model. And then we're going to be doing it for like 2 weeks. This was previously a thing for a guest speaker, but that's in the ropes for it now. We will announce what's going to happen that day, but yeah. And then the latter half of the semester, we're going to be doing machine learning stuff, performance metrics, then release your project sometime in April. So yeah. Yep. Today, so just to, just because there's just so many things in Python that we haven't discussed, these are just some little small tidbits that are maybe useful to you in your journey of, probably going from Java or some other C-style language to Python. Just some miscellaneous tips. Booleans in Python are known as these two values right here. They're capitalized true and false, as opposed to, the lowercase ones you would see in Java or something like that. And believe these are also both objects, right? In Python? Bill?
Yeah, I mean, in fairness, I'm right, everything in Python's an object.
That is fair.
But yeah, I mean, Booleans, yeah, those are objects. Also, I think someone made a joke about this last meeting, but just to reiterate, please do not make a variable that's like lowercase true and then call it false, or the reverse, because if nothing else, you're going to piss yourself off when you're debugging later. But in all seriousness, it's also very, very, very much against Python's style guide. So yeah. Also, another quick tip is I think there's a command you can figure it out on the internet that actually, if you type it into the terminal, will literally just print out Python style guide. So,
Yep. And not is another, logical operator that essentially, negates Booleans. What I mean by that, I'll just show you right now. Yep. Okay. So if I go here, oh, are you guys able to see the collab file?
Yeah.
Okay, cool. So if I go here and if I just take, any old Boolean, this is a true value, gets highlighted because it's, logical operator. If I put a not in front of that, wait, first of all, I'll show you how it is regularly. If I just, run that cell, this outputs what it is, it's true. But if I put a not right in front of that, negates it, becomes false. So this is kind of useful, for example, if you want to see if a key exists in a hash map or something like that, if key, not in, I don't know, the name in the dictionary, whatever name, then you do yada, 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 right? So yeah, that's just kind of a miscellaneous thing that's useful sometimes. Whoops. Yep. So none is, Philip is going to correct me for this. So I know he's ready to correct me on this, but none is more or less kind of the Python equivalent of null. It's pretty different, but effectively it is pretty similar.
What am I going to correct you on? You're right.
But it's not exactly null. It's kind
of... Yeah, sure, but that's all semantics about what null is actually pointing to. So
yeah. That aside, importing and pip installing libraries, this is actually pretty important for our purposes and stuff. Not so much pip installing because of how wonderful collab is, but importing a lot. So essentially, quick run through of what libraries are again, in case you're unfamiliar. So libraries essentially allow us to abstract away complicated functions so that we don't have to implement them from scratch. So oftentimes we'll be using libraries to implement these machine learning models, which under the hood have a lot of complicated math, linear algebra, calculus 3 going on in between them. But all we have to do is just literally call that function and it'll do all the dirty work for us. And to show you what that means in practice. So for example, one of the most, common libraries we're probably going to be going through today is a library called Numpy. So the way that we, sort of get access to all the functions that the Numpy library has to offer us is that we put the keyword import and then the name of the library. In this case, it is Numpy. And then oftentimes you'll see people follow this by keywords like as PD, for example. This will essentially rename your library to whatever you, not PD, NP in this case. PD would be for pandas. But this essentially renames your library so that you don't have to keep on typing NumPy anytime you want to reference a function from there, right? So that means we have NumPy in our environment, right? If we just want to use any function from there, we can just gonna steal this from here above. So I made a list earlier. It's a list actually, right? This list of strings and stuff like that. So one common function that NumPy has is converting a Python list to a NumPy array. And what is a NumPy array, you ask? I will get to that a bit later. But essentially, the way I utilize the function, which in this case is called array, and it comes from a NumPy library. I first use the name of the library, whatever I renamed it to, and then I put a dot, and then the name of the function, and then call whatever parameters I want. So if I just do that, I will get whatever that function outputs, which is just the NumPy array. Yep. Any questions on that?
Also, a quick pro tip is that if you want, you can actually just import specific functions from a library. So if you type in like from NumPy import array, you don't even have to type in the NP at that point. You can just type, array or toys, and it'll do the same thing.
Yep.
Well, I will say, for lots of things, this is not exactly desirable, simply because you're going to be, if you're importing multiple different things and they all have their own arrays, then that's going to be a problem. Especially for some of the machine learning techniques we'll go to, because they're all named the same across the different libraries, but the name conflicts can get to be a problem. However, it is useful in the case of when you're designing your own Python projects and you have multiple different .py files that all have different codes. Usually you may say want to grab like a function to like load in like a specific document from that you wrote in another .py file, and you don't want to have to retype it. So you could do from that file import the function, and then you can use that function without having to put like a dot something dot whatever on it.
Yep, good point. And another way to think of how libraries work and why we need them is kind of like whenever you go to an ATM, for example, if you press a button on a screen like withdraw, for you, all that is doing is, you're telling the machine, okay, I want this much money. But what's happening behind the scenes is that, there's a computer system going like, okay, let's check that this guy has enough money in the account, which type of bill should we give him, et cetera, et cetera. So there's a lot of stuff behind the scenes that we don't even have to worry about necessarily, because we're kind of abstracting it away and just, taking the very simple things, getting what we want. So you'll see how that becomes more important as we go on. But yeah. Cool. So let me check the chat. Okay. So list slicing. So last time we went over lists and how they're like very powerful and stuff, in the sense that you don't have to, they're not as tedious as Java arrays, for example. And we talked about accessing lists, but there is a way to access lists that is very helpful and will become very helpful when you, start working with data frames, which should be today actually. So like it says here, list slicing is a way to access certain portions of a list rather than just one element. And it's fundamental for displaying data in the context of data frames. So for example, right here, we have like a list of all these string characters, not characters, all these string variables. And just let's say we just want to have the entries bacon, tomato, ham. The way we do that is that we give the indices, the range of indices that correspond to, that portion of the list. So in this example, that would be indices or indices, whatever you want to call it, indices 2 through 5, right? So 2, 3, 4. And notice that the first number here is going to be inclusive of the index, and the second number here is going to be exclusive of the index. Because, that's just how it is.
I will say it's a convention in Python that any sort of range that you type is going to be left inclusive, right exclusive. So you include the term on the left, and you go up till like 1 before whatever you can determine as 1 before the term on the right.
Mm-hmm. Yep. And this is just like, formalizing as syntax. You name the list, your initial index, and your end index. And there's actually an option to put a step size. And what that will do is that it will return like the portion of the list you want, but like in steps of however you want. So for example, in this previous example, our step size was 1. It was just like every other one right next to each other. But you can also do stuff like step sizes of 2 and stuff like that. So just to quickly demonstrate that, let's make a list right now. Because it's Valentine's Day, why don't we make a list containing strings of different chocolates? Does anyone want to shout out different names of chocolates so we can add it to the list?
Hershey.
Hershey, always a classic. I can't spell. Yep.
Kinder Joy.
Sorry? Kinder Joy? Ah, yes.
Oh, I love Kinder Joy.
Isn't that banned in the US?
I don't think so anymore.
Oh,
At least I saw some at the Indian store the other day. So yeah.
interesting.
Dark.
Dark, yep, true. And
White.
yes, the answer to, yes.
Can we get a Toblerone?
Oh, that is so underrated.
It is an 8-tier chocolate right there.
Okay, one more. I think we're good.
Get a Kit Kat in there.
Kit Kat, honestly, my favorite, best, hands down.
You
Okay,
bought like
cool.
a pack of like 100 for them last semester, didn't you?
Hey, don't give that away, man. Yeah, so we have our list here, and we're going to be using what we just learned to get certain portions of the list. So let's say I want to get the second, third, and fourth entries from this list. Can someone give me the syntax to do exactly that using what we just went over? So just to clarify, I want Kinder Joy, dark, and white. I want that portion of the list. Just as a refresher, just this kind of syntax. Oh, I'm so sorry. I wasn't even checking the chat. Okay, so someone says, okay, I'm gonna go with your second answer, which was chocolate, square brackets 1:4. Okay, let's see if that works. Yep, that worked. Remember, we start with our start index, the colon, and the end, oops. And then the end index, pretty much just +1, because like, exclusive, inclusive, all that good stuff. Yeah. Anyone, does that vibe with everyone? Did everyone get that? Any confusions? Any, doubts?
Should also mention, just as an aside, for any of you who are familiar with like other programming languages, I think Rust is one of them, and Ruby maybe, but I'm not sure about Ruby. But like, there are other languages where slicing is allowed, but it returns a different like type. So like when you take a slice of a list, it's not like a list. What it returns isn't a list anymore. It's like a list slice or something. Just like for reference, in Python, slicing a list returns a list, and in general, any list operation, yeah, Summer, I can show you that right now. But like slicing a list returns a list, and all of like the cutting stuff that you do to list will usually return a list. So just keep that in mind so that you don't have to like type in unnecessarily typecasting or whatever.
Yep. And just out of curiosity, does anyone
Also, if you use a step size, actually, so were you about? Or,
Yeah.
Summer, were you about to go through that, or?
Yeah, I was just about to do that, so I'll just.
Oh, sorry, I jumped the gun. Then go for it.
Nah, it's cool, my dude. Yeah. So step size is another thing that we can use. So it kind of like tells us like in what quantity we go in. It's specified just to show you right now. So let's just say for the per the demonstration, this is like length is right. So oh, that's the type of it. That's not the. That's what I was not what I was going for. Right. So here I'm saying this is kind of like janky syntax, but I'm saying here that I want the whole list. So going from index 0 to the end of the list, which is index 6 minus 1. But I'm specifying a step size here, which is 2. What that means is that it's going to skip every other entry. So it's going to say, okay, Hershey, skip 1, dark, skip 1, Toblerone, skip 1. So it's going sort of twos if you think about it, right? And if I do the same thing, but I give step size 3, it does the same thing. It just goes in 3. So Hershey, skip 1, white, skip 1, skip 1. That's it. So yeah. Oh yeah, in case you're curious, -1 will just return the last entry in the list.
Yeah, and I think in general, if you have a step size that is less than or equal to 0, obviously if a step size that's equal to 0, I'm pretty sure it's going to get mad. But if it's less than or equal to 0, I think it starts traversing the list backwards. Summer, you can check to be sure, but
that does sound correct. Let me just.
Well, maybe not. Maybe I'm full of crap.
Yeah.
All right. Yeah, I am. Forgive me. Right. Okay. So negative step sizes are just not allowed. You can have negative indices on your slicing, but you just can't have negative step size because I guess that makes sense.
Yep. Oh, let me check the chat here. Okay. Okay, Philip, I assume you answered that. Okay. There also sublist. I'm not sure about sublist. There might be. It's been quite a while since I've formally touched Java. That's like freshman year. So forgive me on my Java knowledge. I mean, let's try it. Would this print only dark? No, this would not only print dark. So let's just go through that just to clear things up. Let me get rid of this. So the reason I wouldn't print dark is that we start at index 1, which here starts at Kinder Joy, and then we're going steps 2, right? So Kinder Joy, skip 1, white. And since you only specified you want like these 3 indices, 1 through 4, it only gets these 2. You don't get dark. So yeah, that's the answer to your question. Yes, it prints the one with the start index if that's inclusive. So if I specify I want it to start from 2, it will start from index 2. Remember, index 0, index 1, and index 2. So yeah, the start index is inclusive of the number you give it, and the end number is exclusive. Yep. Okay, cool. So you may actually use this somewhere in the exercise we do later on, but this whole concept of slicing will come very handy when we go over data frames, like I've been saying to oblivion by now. But yeah, let's move on. So the next thing I want to talk about a little bit, not too much in detail, because Evander will take it up on it next week, I suppose, is a Numpy Raise. I brought them up a bit earlier. But Numpy Raise are yet another high performance version of the lists that we've been using in Python that are often used in ML data science. By high performance, I mean that these arrays are optimized very nicely at a low level. They're actually implemented in C, if I'm not mistaken, Philip. And, you know, the way that they're implemented makes it much more fast and efficient to do many mathematical operations such as dot product, and, you know, I can go on.
Yeah, they're implemented in C. The main point to do with Numpy Raise, which makes them faster, is that if you think about it, I think we mentioned last time that Python is dynamically typed and the lists are independent of type, meaning that I can store a string and an integer and a Boolean in the same list, and Python doesn't care. However, Numpy arrays, ideally, you want every entry in them to be the same type. Now, they can still support everything being of a different type, but then what you'll see is that the array's data type, which is the type of data stored in the array, will be referred to as object, which is just a general class for Python objects. The things that one of the main optimizations that comes from Numpy arrays is that they expect the data in them to be of similar type. So as a result, things like the dot product and, you know, matrix multiplication, just a bunch of linear algebra operations, a bunch of operations in general become faster because the computer doesn't have to spend time checking what's in every element. It just knows what's there. And so it can go ahead and do the operations.
Yep. And as I demonstrated here, the most simple command is to literally transform a Python list, like 1, 2, 3, into a NumPy array. And you do that using the numpy.array function. Like I said, I'm not going to go too much in detail because, like, there's a lot that you can read. There's a NumPy documentation that I put up right here. It has pretty much everything that you would need to know and stuff like that. So, you know, there's a lot of functions and whatnot. You can read on your own time. And I will provide a link, but you guys can Google. But essentially, the other thing I wanted to bring up is how NumPy arrays are, like, you know, designed. So one aspect of these is that they have these things called shape. And shape, eventually, in a sense, it defines, like, the dimensions of the arrays. So recall that we can have, you know, different dimensions of arrays. So we can have 1D arrays, 2D arrays, and 3D arrays. So there's this attribute called shape that will describe essentially, you know, the size of the array, if you want to say so. So for 1D arrays, since you only have one dimension, it's gonna, you know, give you how many elements are there. So for example, one dimension, this has 4 elements. The shape is going to be of 4. And then if we have a 2D array, the shape is going to consist of the number of rows and a number of columns, if you want to think about it that way. It's like how I like to think about it. So in this example, we have 2 rows here. So the first entry is 2 of the shape attribute, and we have 3 columns, 3 vertical guys, which is the second entry right here. So it's going to be 2, 3. And by the way, these data structures right here with the parentheses and the commas, they're called tuples in Python. Yeah, there's just another data structure.
They're the same as lists, you just can't modify them.
Yeah. And then 3D array, we just keep on expanding this logic. So we have, what is it? For the, I'm going to say in, like, you know, 3D terms, because I'm taking Math 241, I'm going to say 4 in the Z direction, 3 in the Y direction, and 2 in the X direction. But yeah, this logic can keep on spinning, but mostly we'll be just sticking to this thing right here, 2D, which is going to be rows and columns. So just to quickly demonstrate, I created a list here earlier. I don't know why I'm copy pasting. It doesn't do much for me, but this is like essentially 2D array, right? So we have a list.
That's going to come out as a 1D array, Matt.
Hmm?
Oh, never mind. I can't read. Sorry, go on. I thought there was a
Yeah.
comma between action and figure. I was like, I don't think that's going to work.
Cool, it's cool. So list of lists, you know, each entry is a list itself. I can print it out, just, you know, normal as day. Now, let's say I want to convert that to a NumPy array, which I've already done, which I don't know what I'm doing, just for the sake of demonstration. So now this list has now become a NumPy array, right? And if I want to check what the shape of this NumPy array is, all I have to do is give the name of it, followed by the word shape. And that will give me the shape right here. So just as we discussed, it's going to give me the dimensions of it since it's a 2D array. 3 is going to correspond to the number of rows. We have 1, 2, 3 rows right here. And 2 is going to correspond to the number of columns. We have 1, 2 columns here, right? So why do we even care about NumPy arrays? Why can't we just use lists? As Phillips very well said, first of all, they're very optimized. And an extension of this, a lot of data frames, a lot of data structures that we're going to be using to store data are implemented with NumPy arrays just because they're so nice. And
In fact,
so
all of them are.
Yeah, pretty much.
Yeah.
But when you use the data frames, we want you to be able to, if you get an error by, I don't know, getting off an index or something, it's often going to look something like, it's going to be based on the fact that all these are, NumPy arrays. So it's going to be based on shapes, for example. So,
Common errors are shapes and data types specifically.
Yes.
So as Samrat was mentioning, shapes will, if you have mismatching shapes, like think of it like, for those of you who have taken linear algebra, just in general know what a matrix is. If you think of it, you can represent the matrix as an array, right? So if you try to multiply like a 3x3 matrix with like a 2x2 matrix, that's not going to work. And so if you tried to do something like that in NumPy, what it will do is it'll return something like, shape dimension mismatch cannot do this operation with dimensions of these, dimensions of the two arrays you give it. Also data types. So if I tried to take the dot product of, or if I tried to like multiply two arrays that both had that both had strings in them, it will invariably get mad because how do you multiply a string? So those are two of like, the more common errors that will happen. Some of the more obscure errors that like you may run into, but I can't really just think of off the top of my head. Those are kind of those sometimes will print out some pretty obscure error messages, but in those cases you can just, ask us or Google and you should be able to find an answer.
Yes, sir. And I just put down here, just like visualize what a matrix is, what we're talking about and stuff like that. And the last thing I want to say is that, shape, I pretty much went over. It's the function that gets the shape array. It's going to be very useful. So before we move on to the data science part, I want to refresh everyone's memory and, bring us back to what this club is about. We're not a Python club. We're not, we're not 131 for Python. We are a machine learning club. So, machine learning is, right here, algorithms with the ability to learn without being explicitly programmed. So how do we learn, you say? We learn from data. We learn from the characteristics of the data. In this very specific example, we use tabular data to, use different attributes, different characteristics, columns, whatever you want to call it, to predict whether a passenger in the Titanic died or not. I think it's usually phrased as survived or not. That I phrased it the wrong way. But anyways, morbidity.
Both work.
Yeah, I suppose so. But essentially, the rough process is that it's going to use different fields, like, what was their name, what was their sex, how old were they, where were they sitting in the ship, and in a way, the machine learning model is going to notice patterns, look at, coincidences. Well, not coincidence, that's a bad way to phrase it. But basically look at the data and try to see if there's anything that makes sense to sort of formalize some type of, in many cases, function. It's going to try to, predict something, and it's going to compare that with the actual result. And in some way, it's going to quantify some type of loss, some type of, how wrong did it get it? So this is pretty much what I'm talking about right here. You have your data about a certain thing. In this case, it was characteristics of passengers on the Titanic. You train it, and by training, you essentially give the data to the machine learning model, and it learns what learning means. We'll get to eventually. But essentially, once it's done learning, it gives a prediction. And by the way, I'm speaking in very vague and very, high-level terms, so I'm not being exact in what I'm saying here. So just bear with me. This is it's like conceptual stuff. So the thing is, learning predicts. So for example, let's say, I don't know, Mr. Owen Wilson. Actually, no, let's not go with the actual name. Mr. Duty Sweet Corn McFizzle was a passenger in a Titanic. Let's say for some reason he was a very young passenger sitting in the lower, cabin, so closer to where the actual ice rammed to the ship, and had like a lower income. So let's just say that the machine learning model, because of these certain attributes, the machine learning model predicted that the passenger is not going to survive. So let's say that in reality, the passenger did survive. In that case, the machine learning was wrong. And in that case, it has to check, did I get this wrong or right? In this case, it got it wrong. And it has to go back. And it goes, okay, what did I screw up here? It has to optimize, right? And it keeps on doing this until we get a final model and that we can test on real world data to, deploy it into the world. And bada bing, bada boom, we have our machine learning model. But as always, the first step is always going to be data, the stuff that we're learning from. We don't have any data, we have no machine learning. That is essentially what it learns from. So before I go off on a tangent, I will hand the mic off to Evander, and so we can talk to you about data science. So yeah.
All right. Hello. Gonna be giving you guys an intro to like some data science. So I got a slide, and I also have like a Python notebook for you. So I'm not sure if you guys have seen it, but if you go to let's see, if you go to the pioneers, if you have access to that, then you can see there's a big think. It's big think week 1 DS. And then there's like a CSV file, watches.csv. So I'm just like start running it for you guys.
I think I'm going to upload the. I'll give the links in a Google Drive so that they can access it.
Okay. And you should probably like screen share and show them like uploading or putting the CSV into Google Drive so that they know what they're doing there.
Okay. Yeah, I don't have access to like the actual Google Drive that you guys have. Having issues with the registrar. Anyways, let me see this. Time to share. Okay. So, oops, this goes a little bit too far. So yeah, intro to some data science, and this is the content that we're gonna have. We're gonna do some importing, some intro to data frames and series, data frame methods and properties, histograms, QQ plots, data frame grouping and filtering methods, and yeah, that's pretty much it that we're gonna cover. So let me. This is just starting off content, so I'm just gonna read off this slide over here. So data frames and series, basically the Pandas data frame is just a 2D, two-dimensional labeled data structure with columns for the potential for different uses. So there's like methods attached to like how you can filter the data frame or how you can like reshape the data frame. And it's similar to just like an Excel sheet. And similarly, like we have a Pandas series, and that's a one-dimensional labeled data structure where you can hold data such as strings, integers, and even like Python objects. And yeah, so let's get to some of the code here. Make sure you, if you want to follow along, just make sure you download the files over there in the Pioneer. That's Big Think Week 1 DS, and if you want to download the watches.csv. Okay, so let me get started sharing the actual notebook.
Evander?
Yeah.
I don't think we saw the transition to the other slides, like when you were talking. Like it was stuck on the first slide.
Oh, okay, so here we are.
Yeah.
Sorry about that. Yeah, so this is like the slide that we're going to cover first is like, so this was the content. And so over here, I mentioned that before. And then we're going to be covering data frames and series right now. And so let me get that started with showing you guys the notebook. All right. Sharing the notebook time. Okay, can you all see this? You see my Visual Studio?
Yeah, we can see it.
I got using VS Code, +1 there.
All right, awesome. So you need these imports. We're going to be using Pandas. So you need Pandas as PD, matplotlib.pyplot as PLT. And I'm not really going to be using Seaborn. I don't know why I have it here, but I kind of just throw them by default. And we're not even going to be using NumPy either, not in this notebook. And so we're going to want to import our CSV file. So what you're going to do, if you put like the CSV file within the same folder as this notebook, you're just going to do like R, like relative path / watches.csv. I got to do this. So I got to basically put in my own desktop address over here. So I'll be using this notebook. So I'm going to be running this and going to be importing. Whoops, what just happened? Okay. Watches. Okay, yeah, I know. I moved that to the desktop. Let me fix that real quick. Give me a second. So, okay, should be good now. So let me rerun this. Okay, check mark. So we're good. And oops. Okay. So yeah, so we imported the data frame here. And also I just wanted to show you guys really quickly that you can also import data frames through URLs. So this is a particular URL that's hosting some really basic data. This is called energy data, but we're not going to be using this. I just want to give you show you guys that you can do this, and by inputting the URL, delimiting some separators, and just for this one in particular, there's no header, so you just mention a header. But anyways, you can download this, open this up, and see energy data. So that's what's on this random data set. So I mean, you can find other data sets online. You can sort of pull them in, but like I said, we're not going to be using this. So the introduction. So the data frames are going to allow you to structure and filter data more efficiently than using just pure Python. I mean, you could do similar things with let's say lists of lists in Python, but that'd be super inefficient. So with just using Pandas, you're going to be using a few lines of code to do operations that involve manipulating your tabular data. And so that's similarly with the series, we're going to be doing a similar thing. It just allows us to more easily manipulate this sort of tabular data, and has indices that enumerate the series in the object. So it's basically just a series is basically a column of a data frame, just to give you a very basic idea of that. Now previewing our data. So we're going to use these very basic. Let me make sure all the outputs are cleared so you guys don't see all the results yet. Got to build up the drama or whatever. So yeah, you do .head is going to give you the first 5 rows of your data set. .tail will be doing the last 5 rows of your data set. This is just a very basic way of previewing your data, seeing what's in there, what type of data you have. Well, not really type, just what's in there. We're going to get to type. And also you can extract the series of a data frame by slicing a particular column. So here, this is I do df price. You put brackets and parentheses price, and yeah, so you can see this is actually a series, and we can actually just double check that too. If you want to see what sort of data type this is, you can just do that. Do type parentheses and whoops. And there we go, it's a series. Yeah. And similarly, you can also extract multiple columns, which will be basically constructing another data frame. So over here, I just, I'm making an instance of a particular data frame that's a slice of basically a slice of 2 columns from like the main data frame. So I'm just extracting price and engagement, these 2 columns, and you can run that and you can get this data frame here. And this is a data frame, not a series. So just want to distinguish that. And if you actually want to see the types of variables that you have in your data frame, or like for each column, then you'd be using df types. So this is actually really important to know, just so like you can know which is your numerical data versus what are like your probably categorical string data, stuff like that. And you can also see the shape of it, just to see like, okay, how many rows do you really have? Just like with larger data sets, you have 75 rows and 5 columns. Now we're going to jump into QQ plots and histograms. So QQ plots, or okay, actually before that, let me make sure we go back to the PowerPoint so we can introduce them. Can we see the PowerPoint? Can I get a check on that? Hello? Okay. I see people can see the PowerPoint. All right, so we did data frames, and we covered a few of the, we're going to be covering a little bit more, but like we'll be seeing set index later. But we covered head, we covered tail, we covered shape and data types. And so here you can, you'll be able to like see this this PowerPoint, so you can basically just check over some of these functions. And I also linked you to the website for like a data frame table of functions and all that sort of stuff, so you can see a whole suite of them, or just review them and review their inputs. But now we're going to be covering histograms and QQ plots. So from this picture, you can sort of get an idea of what histograms and QQ plots are. Histograms, you're probably already been exposed to in some degree. Basically gives you like the frequency of each, let's say, bin of data. And what does that have to do with QQ plot? What is a QQ plot? QQ plot stands for quantile plot. Basically, all you need to know is that the QQ plot basically shows you how normal your data set is, or how normal your data is in general. So basically, how much it corresponds to a normal distribution. The importance of this is because a lot of let's say machine learning algorithms, or like standard practices in data science, require you to have, or optimally would want you to have a normal data set, normalized data set, as in like, you know, it's normally distributed. And so if you see your QQ plot, if you look at like these examples of the QQ plot, you want your line to be straight. Basically, you want this line to be like following this what's essentially the theoretical line over here, so which is just like the straight line. So if you see your data points are skewing off, either upwards or downwards over here, it basically tells you that you have a skew in the distribution of your data. So that's how you can interpret that. So let's go to the actual notebook. Back to the notebook, doing a lot of switching over here. And let's go to, so, okay. Hopefully you guys can see the notebook. I'm not getting much audio feedback over here. I would appreciate, you know, if anyone like has any questions, or if people want me to slow down, that'd be nice. Yeah. Anyways, now to the QQ plot. So we first have to import SciPy, and we're going to be importing, like particularly, we're going to be importing stats from SciPy. So doing that, import stats, and so this was our data. This is the engagement metric within our data. So okay, maybe I didn't go over the data set too well, but like basically it's a data set of watches, right? And the data set of watches has like their model, the store, the condition, the engagement metrics, which is basically how often people are visiting the website to see the watch, and prices, of course. So over here we get like the engagement metric, which shows that it's fairly normally distributed, except for like the tails, which isn't too bad. There's actually methods that we'll be covering later on how you can sort of like improve the normality, let's say, of your data set by making it a little bit more closer to a normal distribution, and it'll like look better at the tail ends. That involves like maybe like transforming or standardizing your data. So, but over here we can see that it's decent. It fits for the most part, except for like at these little tail ends. we have a little bit more deviations. But if we look at our other variable, which is our price, we're going to see, okay, is there some sort of like, what's the distribution of the price? We want to see what that looks like. And what we see is it's not normally distributed at all. It's just like, you know, two different sectors, I guess you could say. It's like, you know, you have like, okay, I see a GDG. Somebody's got to go, but I hope you enjoyed this, you know, this presentation and everything like that. And I hope you do download the notebook and the data so you can kind of like go through it yourself. And yeah, so we feel like there's a bit of a, like a definitely off behavior in our price data, and that like, it's just, there's not really a trend going on here at all. Basically, it's just two groups. And yeah, so you can like, this would basically like say like, well, our price is sort of like split between, you have like watches that are less than 1,000 here, and you have watches that are like around $4,000 here. And let's see how that reflects in our histogram. So our first metric, so the first QQ plot that we plotted was for engagement, and we're also we're going to be plotting this the engagement variable in the form of a histogram and seeing how that looks like if it corresponds with, let's say, a normal distribution as the QQ plot would entail. And we're do this, and look, there you go. It's fairly normally distributed. You do see a bit of a let's call it a right skew. I think it's like, so this is like, yeah, so if you a right skew, oh, no, left skew, sorry, it's a left skew because like that's where the tail is. Okay, but yeah, so this, so we have like our, we're gonna see how to interpret this, but we have like we see that it's fairly normally distributed, as in that like you have this bell-shaped distribution of your data. Now we want to see how to interpret that. How do we interpret this sort of data? I mean, this could actually be made better if we did some like transformations, like I mentioned before. But we want to see how can we just interpret this from like what we have over here. So we have like the minimum value here. We have like in terms of engagement, 67, maximum value 86. We see a mean and median value over here. So mean is like 78.55, and the median is 78.86. But what does that really tell us? Okay. So let's go back to our slide. Okay. Hopefully you guys can see the slide. So the histogram skew interpretation. What do we like? What information do we get from like the skew of a histogram and this like sort of mean median behavior on whether the median or the mean is on like the left or right side of each other? So so if the mean is larger than the median, then the data is generally right skewed. So over here, so that basically is like a few of the values are larger than the rest, which is basically saying right skewed. So what we have here is we have our, we have our median being larger than our, we have our median being larger than our mean. So this is this is going to be like, well, the opposite of this first statement. It's going to be left skewed. So you see, if the mean is smaller than the median, which it is over here, then the data is generally going to be left skewed. A few smaller values bring the mean down. And if the mean and median are close, then the data is fairly balanced or symmetric on each side, but not necessarily bell-shaped, which is what we have here. It's not necessarily bell-shaped, but it's fairly balanced enough that it is within the normal distribution range. Okay. And yeah, should have so this is just reiterating the QQ plot interpretation. I probably should have put this switch the order, but yeah, the QQ plot interpretation here is just the QQ plot. So sorry, the QQ plot is an inferential statistical process. Oh, well, sorry, various like inferential statistical processes and algorithms assumed at normal distribution, like I mentioned before. And so the theoretical line, that red line, is what we want to map to. And Yeah, so if it maps perfectly, so if we have like our data mapping perfectly to like the red line, then that would give us we can interpret as our data being very close to a normal distribution. And so, yeah, let's go back to the notebook. And hold up, I'm getting a message from Sam really quick. Okay. So going back to the notebook. Let's see. Does anyone have any questions, or does anyone want me to slow down or go back over something? Just ask me now real quick. You can, I don't know if you can jump on the mic. If you can. Okay. Any questions? No? Okay. Well, moving forward. So we're going to look at the histogram again for prices. And as you can see, the histogram for prices is also very split. You have these watches again under like $1,000. There's like just sectioned off, like there's high-end watches here at around 4,000. There's these like lower end watches that are like between 500 to like 800 really. So basically what you can kind of like glean from this is that like you won't really be using prices as any sort of predictive metric for, let's say, another attribute of your watches, like let's say of engagement. So like these two are correlate. You're not going to find a like predictive value in using prices to determine some sort of engagement, or engagement to determine prices, just because like there is no sort of like, I guess intuitively you can just see there's no overlap in the shape of your data. So you're not going to be able to like really use them to predict each other. You could potentially use prices, engagement to predict something else about the watches, but we don't have any other variable that we would be using to predict onto or predict it out. So yeah, so going forward, oh yeah, we do have another extra plot over here. This is just another little bonus plot. This is a fancy scatter plot using Plotly Express. And it gives us a nice scatter plot here that also just shows that like there's not any particular trend in our data. So yeah, we're basically just like observing like little clusters here, but there's no particular trend. You have like, yeah, I guess you could feel like, well, there's clearly like these Superstore seems to be doing a pretty good job in marketing their lower end watches, since they're all fairly high, and there's no like cluster of Superstore watches down here, but there's not really any sort of particular pattern that you can extrapolate from here. Anyways, we'll be covering now some logical indexing, or logical indexing and filtering within data frames. And so data frames can be logically filtered for certain features using the function ilock and lock. Yeah, so yeah, ilock and lock. And ilock is particularly used for like primarily integer-based indexing. So as you can see over here, so if I can, let's say if I just do this, then I want like I want rows 16 through 30. Well, it's going to give me 16 through 31, so this is going to be like one less. But I mean, that's not something like too difficult to like deal with at all. So if I wanted 31, just say 32, give me 32, so I can get 31. All right, and like I mentioned, similarly, we can use the function lock to do logical indexing with. So basically, that'll be let's say basically logically indexing based on certain columns within your data frame. So over here, I'm particularly using engagement and condition. So I only want, this is basically just saying I only want the good watches, and I want them to have an engagement metric of over 77, which I guess that's fairly popular, or popular enough for me. So it's gonna give me the output for that, all the rows that correspond to a logical index of conditions good, the conditions being a value good, or category good, and engagement metric being over 77. So here you can see they're all over 77, they're all good. And so the prices, yeah, fairly spread out through, like, there's the high-end watches over here at around $4,000. You have 800, 600, $500, and only two watches are about $500. So that's the low end, fairly pricey. And now we're going to be using, we can also, with our data frames, Pandas will, so Pandas actually assigns a series of numbers as the indexes. That's the unnamed column of integers, and like in boldface, usually in boldface, will be here. Save. Yeah. Sorry. Yeah, so it'll be just like the unnamed column of integers that you can see at the leftmost side of your data frame. And you can set a custom index though for your data frame, and that can be more useful in some instances. So let's say I have some categorical data within my data set. Maybe I just need to use the numerical data, so I can just use like the variables model, story, condition as indices. So this also means I won't be actually able to access them anymore. I'll only be able to access the two numerical columns once I do this. So so I could first I could just, let's say, show you one. I can set model to an index and show you what that looks like. So here it's basically okay. So yeah, we're coming up on time here, but yeah, I'll try to like finish this up real quick for you guys and let you guys explore. So over here you can see model is set to an index since it's lowered, and you have all these other 4 columns are still accessible variables or columns within the data frame. And then you could so okay, and then we can model's now already a index, so we can turn store and condition also into a index as well. So you have now you have two store and condition. Yeah, now store and conditions are now also indices. Yeah, so we are coming up on time. We can cover, let's say, hey, Samra, can we be covering the rest next week with
Yeah,
grouping and pivoting?
Yeah, we can continue next week. I just want to say, yes, so thanks for coming, guys. I just pasted a link to the feedback form for today's and last meeting's looks like a feedback, yeah, pretty much for that. This is like the first of, I think there were like 2 more, one in the middle of the semester and one at the end. So just like the beginning feedback form. Please, please, please fill out the feedback form. It has literally shaped this club and it has made it what it is today. We've made many different changes. Oh yeah, last semester we got a lot of feedback, so that like to include more review, and that is what caused us to make the first 15 minutes of meetings into recap sessions. So feedback forms kind of in a way structured the club. So yeah, I'm just trying to emphasize the importance of feedback forms. I will say it again, please fill out the feedback form so that we can assess how well we're doing, how well you guys are feeling the club and stuff like that. Yeah, it's really good stuff. Any words of praise you'd like to get? Oh yeah, by the way, sorry, thank you so much, Evander, for the deep dive into data. We will be going over more of that next week. But yeah, Philip, any words of praise for the feedback form?
Please do the feedback form. That's all. No, nothing else there. We need it so that we understand how to tailor the lectures to you guys so you can better understand what's going on here. So yeah.
Lectures? These are meetings.
Oh, same thing, same shit, different toilet. Anyway, all right.
Evander, any words from you?
Yeah, just do the feedback form, please. That would be great, so we can improve the quality of our presentations for you guys and making sure you're getting the most out of it.
Relocating the
Alrighty. On that note, I got a dip because I got a class now. So I'm assuming it's fine to cut the recording here. So see you guys.
Yeah.
Yep.